your desk from, computers, cell phones, and tablets, whatever. Just have a piece of paper and a pen. So, how is do I need to turn off the light, or can you see okay? Is it bright enough? Easy, I will zoom in. A little bit of reflection, a little bit. We'll see. Okay, so the course is, as I said, it is based on real good knowledge of some things that are calculus, and just about very hard to point out what's not there, what is not in calculus 1 and 2 that will not come up. It's hard to point it out. Okay, so I right now I can probably point it out right now, but there must be something. So it is a challenge, and then the primary challenge will be, however, is the goal, the main goal is really modeling. Okay, so setting up differential equations. So setting up problems from what basically is a word problem. You might remember from calculus 1, frequently that is the challenge. Okay, so to find mathematics, especially calculus, not kind of algebra, but actual calculus in verbal description of a phenomenon. Anybody has done it before? Any remember any examples from calculus that a description that is entirely verbal, and then you have to actually then produce some kind of model? Calculus, pre-calculus, maybe.
Optimization problems.
Okay, yeah, optimization. So an example, something. I mean, it's not technically a phenomenon, but it is a word problem. The challenges are pretty much the same. So you have some silly problem. I would pick as a you have a piece of cardboard. You cut out the corners and make up a box of the largest possible volume. Okay, so why did I say phenomenon? Because what we are doing here is primarily for a large part of the course, maybe the whole course, it is a phenomenon happening in time. Just you may have noticed that most of the application calculus 1 and 2 are processes that are happening in time. Okay, so that is a slightly different. Slightly different.
So you're talking about projectile motion?
Oh, sure, yeah, exactly. That would be one example. So the problem could be, well, Newton didn't know hypothetically. So how do we describe a motion of a cannonball shooting forward, and then describe the trajectory, or maybe aiming and so on. So we'll definitely look into that, even though you've seen this in calculus, and maybe even in high school, remember, but it just usually comes from, the formulas are known. Okay, so that's the easy part when everything is known. But here we have to be slightly more specific, and that is maybe we know something about the setup, meaning, for example, forces. So the gravity would be an assumption which lies outside of the scope of mathematics to make a part of a problem. Okay, so which is what the assumption is. Well, there is a one unidirectional constant force. Okay, and mathematically speaking, it's really not what is a force. We don't care what force is. It's acceleration. Okay, so acceleration is constant in this direction. So what should the motion look like? Okay, so that's the setup, which is very much what we're going to be doing. But I just wanted to see that's certainly Newton was thinking that. we are well beyond that. And examples that you must remember from calculus, how about population? What am I talking about?
You're talking about exponential population?
Well, exponential would be the answer, right? So exactly the point of what I'm trying to make is we'll be right now setting up things, okay? Rather than finding the answer would be the biggest challenge of a kind of modeling or any word problems is actually to set up the mathematical problem. Then usually you will figure out what to do with it later. So then you set up the model for for population growth. You set it up. You do numerical analysis. Possibly we're going to do that, and then simulation. And then you realize, and then you solve it. Okay, with your knowledge of calculus, and then you produce the answer. And then at the very end, you say, well, that's exponential. Okay, so it is. When you know the answer, it might sound roundabout, but really, it is not. That's our plan. Anyway, so let me first point out something that is what takes us away from calculus. What is that new here? And that's a little preview. Okay, so there's setup. Let's look at the what's on the left first. Okay, so we have time and directions. Okay, so we're moving through a field, and then we're moving according to time. We know in which direction we make a step. East, south, west, north, and then 0, meaning we do not move. Okay, so list of instructions as they depend on time. So is there any doubt that you can execute these instructions, right? Okay, so does it remind you of anything in calculus 1?
Vector field?
Well, actually no, but I hold that thought. So moving east indicates the direction, right? And assuming that we are making one step at a time, it is direction and as well as how far you move. What's the word for it?
Distance?
Well, no, actually it's velocity. How fast per unit of time and how far, but with directions. Okay. Naturally, in calculus 1, there's only one direction. That's why there's only one number to worry about. Basically, we're moving through a field, so I could execute it fairly easily. So I move east, then south, west, and then north, and then I don't move. Okay. So the analog of this is the velocities, except they're what do we call this? What I just drew here. What do we call it in either early calculus 3 or the end of calculus 2? What do we call this? Mathematically speaking. So you can call it a path, you can call it a trajectory. What else? What's the mathematical term? As your location depends on time. That's what it is, right? So in time 1, you move to this one, and then all these are the locations. The arrows are listed here in the second column, but then actually what you end up with is a sequence of locations, right? So this is actually my path. Okay, so what's the mathematical term for this? Location as it depends on time. In dimension 2. We are moving on the plane. What do we call it?
Is it displacement?
It is, well, each of them, so I call them velocities, and it would be fair also them to call these little directions as displacements, again, so that's fair. And you can also describe each of them as a vector, indeed, vector. But altogether, we did not. That's what that table is, just a bunch of directions and vectors. But once if we concentrate on the red dots, the displacements are gone, and what we call this is called a parametric curve. Sounds familiar? A parametric curve. So who is seeing parametric curves? In calculus 2 or 3, right? So, okay, so in other words, literally, location as it depends on time, so in two-dimensional situation, it is in fact points at a time, two numbers, okay, indicating the coordinates. Here, as you can see, I have started with an arbitrary point without labeling, and so if I choose a different initial location, what's the difference? Just to test your knowledge of calculus. If I pick a different initial location, what effect would it have on the path?
Change the pattern if you change the start location, wouldn't it?
Yeah, so it will change. Okay, so it will be different to begin with.
It would translate.
The question is what is similar, and the answer is
It would translate it.
it will be the whole path will be simply translated, shifted. Okay, so for example, I could, if I start over here and then I go once again this way and then that way, directions are the same. And then I come over here, right? So my locations are then these. So that's the translation. Where is the translation? This is the translation. I'm out of colors. Let's pick a green one. This is the shift, the translation or the shift. Okay, so the whole path is shifted. Okay, and the only answer is, I once again, remember in calculus, what letter should I assign to this green arrow? What letter should I label it with? Okay, I'll give you the answer and you tell me why. Why is it? Why do they label it with C?
Is it the integral?
That's right. It is the integral. Remember plus C in the integral, right? So you integrate, you produce one function, but then how do you find all the rest of the integrals? And the answer is you add C. So this one, except in contrast to dimension 1, this is two-dimensional, but the rule remains that path that you drew from what amounts to the derivative will produce a new curve, will produce a bunch of curves, but they all differ by a constant. A constant which happens to be not a number as we used to in calculus 1, but in parametric curves, it is a vector. So, but nonetheless, the exact same path. So like this, and then you shift, and it's exactly the same shape, but except translated. Okay. So that's something that we'll get to later because I decided to start with a two-dimensional example to make the point because it's more visual. But in the beginning, we'll stick to dimension 1 entirely. So we will be staying within calculus 1 for the most part. So let me make the point. And so that presumably, why do I call it old? Because it's all falls under calculus. Maybe not calculus 1, maybe 2. But it's still calculus. So what's the difference with when we were to speak of differential equations? And this is on the right. It kind of is similar, but there is no time. Okay, so we have as it was just brought out mentioned, a vector field. You can describe it as a vector field. So if you know it is a field of vectors, literally, so if you know where you are in this field, you know which way you're supposed to go. You see? So if I'm right here, if I'm here, which way do I go? I go south. And then I have to go south again, and then I go east. Okay? Is this right? And then I go west. Then I go back and start go back and forth, roughly speaking. So I go south here, then I go east, and then south, and then west, and then I'm stuck. Okay, so the end result is the same in the sense it's still a parametric curve. Your motion in space through time. But as you can see, the initial setup is different. So it is a literally, if you want to express and use words of calculus, it is that you're given the derivative, you integrate it. Doesn't matter what the dimension is, this is 2, and then it's still, this counts as integration. So this is what I have produced here, this is integration. Okay, so the list of directions happens to be incremental. Okay, so we start with incremental. You know, when you do modeling, you want to start with incremental. So the motion is incremental, but nonetheless, in essence, what we're doing here is integration, and then we produce the path. So if you can integrate it, whether numerically as I did, or you do it using your skill in integration, doesn't matter. The end result is pretty much worked out in this manner. So, so like I said, let's not be concerned too much about the two-dimensionality if you haven't seen particle curves yet. So we'll plan to, and the difference is just to be pointed out as what differential equations, how they fit in the calculus. There is no integration. There is nothing to integrate. There is no derivative. Okay, so derivative is whenever I could write here sine t. You know, sine t, then I integrate, I end up with negative cosine t. Okay, so that's plus c. That's your integration. So if you do it in 2 dimensions, what's the difference? What's really the difference? Instead of doing 1 integration, you do 2. You have 2 dimensions, you integrate 1 component function, you integrate the other component function, and you produce all the motions you can think of, and you have a rotation, you can have motion of any kind, as long as you have the derivative. Okay, so if you sort of have a plan, if you like, which is what I'm trying to suggest here, by the way, the paths plotted out, it's like a plan, like a dance, let's say a dance, okay, and when your score tells you when to do what, okay, so that's what it is on the left. When to do what. In contrast, what's the right one is where to do what. Okay, so in the first case, if you know the time, you look at the time and you know what to do. Okay. In the latter case, if you know where you are, it's it's once again some kind of script or events, and then on the floor you have these arrows and you know which way to go. Okay, so the difference is principal. If you want to think of the once again as it was mentioned, it is like a vector field indeed. So a typical example of such a motion would be in anything practical, not practical engineering. Let's say it's a flow of liquid. Okay, so this is, I think, incremental because it's so easy to actually do it by hand without actual computers or anything like that. So, so by the way, so what majors do we have here? Math majors, anyone? Okay, math majors, physics, computer science, engineering. Okay, so well, mostly engineering, but so engineering is whether you're doing modeling or not, it's the ability to do incremental things is crucial, and so every model or simulation will be executed initially as an incremental motion, such as either left or right, doesn't matter, and then we will progress to try to use calculus and solve the problem, you know, in a form that will be more satisfying, but sometimes it's impossible. So the reality of problems that you face and the reality of and the way calculus is designed as a discipline within you know mathematics don't match exactly. So you pick problems that in calculus, you pick problems that you can solve. And then the problems that you cannot solve, you don't never see. So nobody will give you a problem and then you realize you cannot solve it. So why? You know what I'm talking about? So it's not that the problem is difficult, but the problem has no solution. What am I talking about? In calculus. what problems in calculus have no solutions? Well, let me narrow down for you, integration. So, did it come up? So you have a test, you have a problem on the test, you integrate it in calculus 2, and you solve it, and you're happy, and it might not cross your mind that somebody picked the problem that is solvable in the first place. It has a solution, and that's the only reason you put your skills into it, and then you solve it. But the problem, there might be a problem that no matter how much skill you've got, you cannot solve it. So does it ring a bell?
Something goes to infinity.
If you mean functions that are not integrable, then no. It is slightly different what I mean. So there are not integrable functions, and they're technically the function is not integrable, and the integral it's a limit and doesn't exist. So that's not what I meant. I meant for as an example, and I will bring it up again. Is this one? Have you seen this before? So have you tried to integrate it? So it's not by parts, it's not by substitution, and it's good to know that this problem has no solution. Technically, there is no solution to this problem. So a very simple problem. It actually describes the normal curve that you must have seen this before. It looks like this. So it describes distribution of things in life, such as maybe heights, weights of people or whatever. And then if you were to do probability with such a quantity, then its distribution of would look like this. So somewhere in the middle there is the most popular height, for example, and then at the extremes you have very few people at the extremes. And then you need to integrate it, and you cannot, because there is no function at the end of this computation. There is no function. So they actually made up a function. They made up a function for this. We need to integrate it, so let's make it up, because none of the functions that we know, exponential, trig, whatever, any combination of functions do not fit here. So it will not, no matter how much you try to walk around, the end result is none of the familiar functions nor any of their combinations. Okay, so that's what we call an unsolvable problem. It's like same thing if that helps. You try to solve equation x squared is equal to -1. No matter how hard you try, there will be no solution. Okay, so they made up complex numbers to we also might have time for that. So we need a problem, and that is a practical problem, even more practical than complex numbers. And so the problem is not solvable, but nonetheless, if you have a good setup of your phenomenon, and that happens to be described this way, you could approximate. Okay, so then that's why we're going back into something rather than doing the computations in this manner, doing calculus in that manner, we go way back to the definition of integral as, what's the definition of the integral?
The sum of.
The limit of, yeah, the sum of the Riemann sum. Okay, so which approximates, and so if we cannot produce one single formula for the answer to our problem, well, at least we could approximate, and that's what simulation is all about. Whether or not there is a solution or not, you're probably a good idea to start with some kind of simulation which approximates the reality if your reality is continuous. On the other hand, if your reality is discrete in the first place, then who approximates whom? So that this approximates the continuous curve, approximates the reality of a function that is actually a step function. Okay, so in other words, you have to do both either way, and which one is more important is hard to point out in the beginning. Okay, so that's the outline of what's happening. So once again, both of these are the setups. Setups are the directions. You can speak of them as displacements. You can think of them as velocities. You can think of them as the derivatives, except derivative on the left depends on time, on the right it depends on space. Okay, and that's why the integration, you cannot do into this, you can do this, you might encounter this. when you have to integrate and function happens to be e negative x squared. That's not it. That's not that. This is differential equations are more complicated because the function depends on space, not time. So and that's what it is. Time gives you the direction, or space gives you the direction, and therefore the problem is entirely calculus 1, 2, or 3 is out of place here for the most part. So so we know when, we know how fast, and can derive where. Okay, we'll review that next. So calculus 1 for the most part. If we know where, we know how fast. That's case 2. So that's the actual differential equations, apart from everything else in calculus. Can we derive where? And the answer is yes, but it is very hard. Okay, so it is a big challenge. Okay, let's take an example of this motion, and once again here I'm going to one-dimensional situation again. And so this is the simplest situation is. We imagine we are planning a trip that specifies the speed at every moment of time. So whether this trip is on the plane, you're hiking through the woods, or you are driving and you want to drive at different speed, different time. Okay, either way. Okay, so in this particular case, as you can see, what's happening is the velocity might be constant, in which case it is simply you will progress in a very predictable way, or you going on, you have a different plan, and then there is no formula. Okay, so naturally, if you do any kind of physics, then there is a formula. Physics meaning nature. So you choose some kind of formula of change of the velocity, and that will produce trajectory for you. So once again, not to keep it too complicated and not think in terms of continuously changing velocity. That's the challenge of calculus. So let's put that aside for now and just look at whatever velocity is in this particular case. As you can see, is very simple. It's look at it. It is time plus 2. Okay, whatever. It depends. It means that in the beginning the velocity is 3, then it becomes 4, then it becomes 5, and so on. So that's the two columns on the left is time and how velocity depends on it. But now we are computing the location. Very simple, and you may have seen that in calculus 1. You just do addition. Okay, so you choose. That's the choice here. Here. That's my choice. Once again I choose to start my trip at location 1, a milestone, say. And then the velocity is 3. So during the next hour, for example, I walk for 3 miles, and so I end up at location 4. 1 plus 3 is 4. Okay? And then the velocity is 4. So displacement is 4, and therefore 4 plus 4, right? 4 plus 4 gives me 8. Okay? What's next? Time 3. What's the velocity? 5. Location? What? 13. 13, and on and on. As you can see, unambiguously and very simply, you can produce every location into the future indefinitely. Naturally, at some point, we're going to ask the computer to do this. It's so routine that it makes sense to ask the computer to do it for us. But otherwise, there is no, and that usually is the good best case scenario for computer usage is when you understand perfectly well what's going on. You just don't want to do it, repeat it 100,000 times some certain operation. Okay, so okay, so that's once again case 1. Calculus. Let's say old, if you want to really name things here. So I'll name, disappeared again. So I'll name this calculus, and I'll call this ODE. Okay, so that is a case of calculus. Just addition. If the time was spread out at different intervals of time, you might have to multiply. So you multiply velocity by the time to get the displacement. But otherwise, once again, it's no trouble. So it's still one-dimensional case, but now we're looking at ODEs. Once again, one-dimensional, so we're not worried about it. We're thinking about not the flow on the plane, we're thinking about the pipe. And once again, at every location, not at every time, we know the velocity of the flow. Okay, and so now we drop something in the flow, and we want to see where that object, how it will flow through the pipe. Okay, so the computation is just as simple, but to be appreciated how different it is. So hypothetically, once again, I'm making it up, and let's say velocity is twice the location. So here was time plus 2, and here is location times 2. Okay, so doesn't matter. I don't want to make a picture here. Just let's just do computation. So then once again, I do not have a table, pre-computed table. So here I could go on with this on and on because it goes on 6, and I can continue on without worrying about what location here is. But here it is actually the pre-computation of the is impossible. We don't know where to look up the velocity. We have to compute it every time. So as you can see, if happens once again in the box, so it's my choice. That number 1 is my choice where my trip starts. So suppose we start at location 1, which means the velocity is 2. We take that 2 and we compute our next location, which is 3 because it is 1 plus 2. Okay, like this. 1 plus 2 gives me 3. Okay, so knowing the location that is 3, now I compute my next velocity, which is 6. So 3 times 2, 6 is the velocity. And then once again, and then repeat on and on. The next velocity is 6. Next velocity is 6. So my next location is 3 plus 6 is 9. Okay. And then once again, the velocity is computed from that location, which is 18. Well, let's write one more. So times 3. Where's my location?
15. 20. 27. It's 8, 9 plus 18.
The velocity is 18, location is 9.
It goes 27 velocity.
What?
27.
27? Yeah. Okay, and then you go on and on. The next velocity will be 54 and on and on. So once again, it's unambiguous. Computation can be executed forever, as well as the accuracy can be improved if we, instead of progressing one moment at a time, one say minute at a time or second at a time, we can split it into smaller pieces, and we still can carry it out effectively. So it appears that the two problems are solved very much similarly. The difference is, though, that the similarity only exists when we're doing incremental motion. Okay, so when it will all fall apart when we try to deal with the continuous motion, which is what calculus traditionally is all about. So you can make up your own example. So this one you can even try it once you plot what's happening. You can describe what the motion is. So you will be moving away, in this case, farther and farther, faster and faster. And what would you describe? What kind of phenomenon could this be? The velocity is actually faster the farther away you are from the origin. When you think of motion.
Free falling,
gravity. What?
Free falling.
Free fall, yeah, exactly. Why not? I mean, whether or not it's exactly, where is it free fall or not, we don't know, but it is similar because once again it starts at 0, but then accelerates. Of course, the dependence on time of free fall is what is. It doesn't matter where you start. The fall will be the same. And here, if you start, you can start elsewhere, and then you will be having a high velocity right away. Well, anyway, so that's the similarity. Okay, so that's the one-dimensional space. Once again, I throw in something that we have to throw in, and that is the possibility that time varies, the interval of time varies, whether or not, because maybe the data comes into every half a second instead of a second, doesn't matter, or we just trying to have a continuous phenomenon and we just want to improve accuracy. So remember how it happens. It is, we have to multiply by time to produce the displacement from velocity. You have to multiply by the length of the interval. Okay, so so this is the setup that I want to put forward usually. So it's a broken speedometer, and how do I find out that how fast I'm going? And the answer is you multiply, you rather divide distance by time. So you look at your odometer, and every moment of time, whatever the length is, divide by that time how much you have progressed, the distance or displacement. And once again, a good word to use a lot. Divide by time, and you have your velocity. In reverse, your odometer is broken and you want to know where you are. So you use your speedometer and just multiply your velocity by time. Okay, so so 1 and 2. What are we talking about here in the context of calculus? You know, enormously simplified. What are we dealing with? Velocity, also known as what?
Like the first derivative?
It is, yes. It just happens to, because this is like third grade. There is no variability. We assume that the velocity doesn't vary from point to point, and then that's how you compute it. If the interval is given, you just take the distance you have covered, divide by time, and you have it. That is the computation of the derivative, or at least the difference quotient, okay? And its limit is the derivative when there is a variability. So, and then number 2 is,
Like an interval.
it's the integral, right? So the missing part is summation. But once again, if there is no, if we are interested how much we have progressed during that period of time, we don't have to do addition. We just multiply. Once again, speed, velocity by time, and then we know how much we have progressed. Okay, so once again, as I said, that the same stories that we have in here, except we assume it in the beginning that the interval of time is 1, and that cannot certainly continue on forever. And so this is how you actually how things come into play. Okay, so these are the formulas. Once again, third grade really. And then so let's examine that the same 2 problems. So now once again, we review of the is of calculus versus ODE is finished, and then what follows is just a review of calculus, or the relevant part. Okay, so but more in depth. So we'll get back to ODEs as soon as we can, but let's review things once again, starting with third grade. The idea of calculus is there. Okay, here I'm doing what's relevant now, but still thinking about derivatives and integrals, and that is what if there is variability of the velocity from moment to moment, which means that the computations will be not only including division by the time increment, but also there will be a lot of them executed. Okay, so as you can see, what I have here is I have my odometer available, and then I have recorded a bunch of locations, and I want to know how fast I was moving. Okay, so once again, in this case, time is progressing 1 at a time, 1 minute at a time, which means that the division is by 1. But this is, I hope, looks somewhat familiar. So the data is initially in a table. We'll put it in handwriting, and then because the formula is really simple, but it has to be repeated many times. What do we use a computer? Okay, you can see what I'm using here. I'm using Excel. Okay, so for two things to begin with, one thing I wanna visualize it. That's it. Okay, so so I have on the left is that the 2 rows here are moved into here to make 2 columns because it's a spreadsheet, so it's just more convenient. Okay, so time versus location. Okay, and then I just click. Everybody knows how to use Excel, right? So you highlight. How did I produce this curve? From the data on the left. Excel, if anything, if you learn Excel, you won't be wasting your time. Highlight and click insert chart. Just as well. Let me look it up. Where's my Excel? Here's Excel. Okay. Blank. Okay. Okay, so I put, well, let's do it one time. So time here, space here, say y. Okay, so time is starting with 0, 0, and then the next one is plus equal to, so you got to write formulas if you will plus 1, so let's keep it simple. Okay, so down. Okay, so I produce so 21 moments of time. And so you can give me any formula. That's the thing. Excel doesn't care about computers, so that doesn't care about formulas. Any formula will be plotted, so it will produce points, produce pairs of points, and they will be plotted. Okay, so any formula that you can think of. Sine. Just sine. Okay. Sines. So inputs in the first column, outputs in the second column. Okay. I just compute a bunch of sines, and then I'll highlight. Okay, and I go insert chart, and specifically scatter plot. Okay, so that's your motion, that's your trajectory. You could choose different ones with, you can connect them by curves, but that would be misleading because it is a guess. All the connections are guesses. This is the truth. Every point is plotted, and then this is where you have been, and then so that's the truth. That's the data that you've got. Okay, so. All right, so that's my data, and then what is that? So that's just reflects the picture that I have here. Okay, so it just happens to be slightly different, and then the point is to describe what do we see here. You can try to describe the motion by looking at the by just looking at the graph. Okay, so can you describe the motion? What's been happening here?
Slow increase, an increase.
And, yeah,
And then
what?
it's an increase, a decrease.
Increase and then decrease. And if we were, okay, so if we were driving, then what has happened?
Slow down.
What?
You stop, like you're going to a stop.
Yes, it's driving forward, then slow down, stop, turn around, and then accelerated backwards. It is visible from the picture, but how do we make our life easier without that insight and examining the picture? We always prefer to have methods that will later teach the computer to do. So what you just did here, you were looking at the graph and you saw something, and then from prior experience or otherwise, you made these conclusion descriptions. But that's very hard to give to a computer as instructions. Okay, so what do we do instead? What do we do?
Critical points.
What?
Like critical points? You find like critical points?
No. We look at we compute the losses, what we just did, except over here it was exactly 2 points. Over here, 2 points. One moment, the other moment, and we find out how much we progressed, and we found our velocity roughly. Here we do the same only for each 2 consecutive pair of locations. Okay, so you can already compute them if you want to, because every 2 points they're discrete. It's not a curve. Once again, our data gives us this and nothing else. We're not connecting them. So each 2 points are separate, which means I can take them. You can look at the rise and the rise or the run will give you the velocity. And so at every moment of time, the velocity is there and can be computed. So in contrast to eyeballing the graph and telling what it looks like it is doing, first of all, it's not in depth. There are issues there. But secondly, even this superficial description is not something that the computer would do for you without computation. So what computations? These are the computations. We compute the velocity, and then let the computer just tell what they are, the velocity, rather than being more kind of a more guessing game. So every pair of numbers is plotted, and then how fast we're moving, we are. But by the way, every time I asked previously, what if the phenomenon? It looks like free fall, right? So if you're driving, once again, we just described it. But if it was a motion of an object, you might say that description actually fits the description of free fall. Slow. You throw it up, it slows down, then stops at the top, and then goes down. So, but can you guarantee that it is free fall or not? And you cannot. But maybe with a computer, we can be more specific. Okay, so if we compute velocities, how? Well, the way we know how. We know how. If we have the data, we have two consecutive locations, and we can compute the velocity for every interval of time. Okay, so like this. So we don't have to divide this time, so we just subtract, and so this is the subtraction. Here I do it by hand. So 0.1 minus 0 is 0.1. Look at it with this is what's happening. I just do it by hand just for practice. And then 0.2 minus 0.1 is 0.1. Again, 0.3 minus 0.2 is 1.39 minus 3. And that's how I'm producing the velocity in the second row. Once again, tiresome. Elementary, but tiresome and routine. So let's let computer do it. And so if you haven't used Excel, so that's the good idea. So you might read what I'm talking about here in this little example. But instead, let me just show you what I have here. So the question might be the same. So motion is different. The formula is different. Forget about the formula, by the way. All we've got here is the data. Okay, so. All right, so what do I do? So here I want to have here is y prime for the velocity. Okay, so each two consecutive numbers will produce one velocity, which means that this entry, what's in this, the highlighted cell? What will end up to be in the cell where I am right now? This one.
C4 minus C3.
Well, no. I mean, you could go that way, but I'd rather have nothing, because that is it corresponds to the beginning of the trip, which nothing has happened yet, and you cannot compute velocity, but rather do the computation that you have and put it in the second cell. So then you can see that in the beginning there will be a gap, because there are one more locations than velocities. Okay, so now let's carry it out. We just subtract. So so what do we do? Subtract. So equal to, that's the formula, and then what? Indeed, C4 minus C3, but it is better if I just click, so I don't have to type anything. I click this minus that. Okay, did you follow what has happened? Enter. So the velocity was 0.84 during that period of time. Once again, the idea is, rather than typing, if I have that formula, the formula is relative, which means that I don't have to retype it every time. It will be copied appropriately. So if I follow it down and produce that formula, look at it, it does the same thing, only as you can see, one step down. Okay, so the same exact formula, but rewritten by a computer for you, for your convenience. And then I just do the whole thing. Okay, so instead of having 21 or 22 points allocations, I'll have 21 velocities. Okay? And then I could, so these are the velocities, and I could actually describe it rather than look at the trip is kind of complicated here. So if we try to describe it, we might. Maybe we want to do it, maybe we do not. But we're looking, what computing the derivative gives us is simplification. Okay, let me actually maybe make it slightly more presentable. So by looking at the last column, our life is much easier because if the number is negative, what does it mean?
In decreasing slope.
We're moving in the opposite direction. Okay, positive forward, negative backwards. If the number is close to 0, we are pretty much standing. So might be here. So this is, you can also say slow and fast based on the actual numbers rather than trying to examine the graph. We're not examining the graph. We're ignoring this graph. We're taking the data. Okay, and so that's the description of the velocity. And I could also plot this. Can you predict the plot of the velocity? What it looks like? Anyone?
It'll be translated just a little bit
Yeah, how do you know?
because the derivative of sine is
Is
cosine.
cosine. Okay, so if this is kind of sine, even though kind of simple, the velocity should look roughly like cosine. So here it is. Okay, so cosine. So it's almost the same when we shift it. So this starts at 0 and then go up and down, up and down. This one starts high around 1 and then goes down once again, doing up and down, very similar. So you can just put them next to each other. You can see how similar the two graphs are. Okay, so as you can see, that idea from calculus 1, that derivative of sine is cosine, is recovered here in a manner that is very, elementary. This is other than Excel. Somebody created Excel, but otherwise our computations were what? Subtraction, period. We did subtraction, quite a bit of subtraction. We didn't do it. We did it once, and then computer did all the rest of the subtraction, and then we can now describe our motion much more simple by looking at the values of the derivative of velocity, whether it's positive or negative, who tells which one we are moving. If it is a more complex motion, that will become even more beneficial. And where the benefit is especially pronounced, what if the formula is crooked? Some complicated, it's not sine, it's something very complicated. You don't want to differentiate it. Maybe you cannot differentiate it. Maybe it is we are in the other, the second, the actually ODE setup, and then there is nothing to be differentiated, which means that that is not a possibility, but this computation is always a possibility. I can put anything I want in that second column here, and that computation will go through. Okay, so we are independent of the complexity of the situation. We can find the velocities any time we want in this really trivial manner. So once again, if you were to learn how to use Excel, here I'm using a slightly different notation here. As you can see, I'm going to change that to a more mathematical because when you do Excel, anything computational with Excel, you have to sort of have coordinates of the cells within the spreadsheet, and then normally they're like this, C1. So this, for example, this is C3, but it actually I would prefer rather to have it like 3, 3. Okay, so the coordinate as if it's a coordinate system. Okay, so I find it more effective. Okay, so any questions about this spreadsheet, this computation? So you can imagine if they are so far apart, what if I make points close to each other, and then you actually will have curves. Okay, even though computationally, what's the difference? It doesn't make any difference. The computer won't know the difference. So we'll see all of that, and we are still solving the problem that goes in one direction, and that is from the locations to the velocity. This is the computation we just carried out. The dependence is very predictable. 2 points produce one velocity, then the next 2 points produce the next velocity, and on and on. So this is and then I plotted it. Okay, so I do what I just did for you with the spreadsheet. This is the example that is in the text with this, what we started with. So this is the graph we described the motion by means of eyeballing the graph. Okay, that's fine. But now the better way, maybe, once again, the question, is it free fall? Maybe. So, and then what we do is we compute in the last column, the green one, we compute the velocities in the manner you described, and then we plotted it. Okay? That is the difference. That's what delta stands for. From observations, we produce a summary of the motion, okay, based on the velocities. So, what's the conclusion? Looking at the second graph, not the first graph. you make a conclusion that we have been unable to make. And so the question that we have, is this free fall? So once again, goes up, slows down, stops at the top, then starts to accelerate down. That's what the graph in red is that we recorded from observation. That's what it looks like. The description that verbally that we produced, might be describing free fall. Now we did more. We computed the velocities. So what is the what's the verdict?
No,
No. Why not?
because it's starting to lose back around at the bottom of the velocity, it's about to speed back up.
Can you be slightly more specific?
It's not continuous, or the velocity is not getting accelerated at the negative.
Oh, that would be, yeah, that's right. So free fall, the force of gravity is there forever. So you will keep accelerating, in fact, at the same rate, right? So, and this one, look at it, it's not slowing down, but it's not accelerating anymore at the end. Okay, so if we were to ignore, let's ignore this part, what would this describe? So it's not a free fall because there is no acceleration, it's stopping. Can you think of a phenomenon that would describe this?
Terminal velocity?
That's right, terminal velocity, right? So free fall, but with air resistance. And so you're, at some point, because you're accelerating at first, at some point your velocity is so close, is too high, the air resistance is increasing, and therefore it balances the gravity, and then there is no acceleration, and then that terminal velocity would continue on. So what does the graph look like if I try to continue to the right?
Just
It will be flattening out, right? So it's not a literal flat, it is, what's the right word for it? Asymptote, right? Horizontal asymptote. That's terminal velocity is the horizontal asymptote of your velocity. Okay, so so as you can see, that's hopefully the point of the computations, rather than eyeballing and kind of qualitative analysis of the original picture. We tried to analyze this. Now, what if we compute, and we did not, we're unable to discard the hypothesis that might be free fall. Now we have. Why? Because we carried out these computations. So it's entirely starting with observations, then the simple computations produced a summary, and that summary was, we were able to actually identify what's going on. Okay. Okay, so once again, the notation you remember from calculus, these are deltas. If division is also involved with all the difference quotients, and then backwards, if we were to go backwards, okay, so that, remember the flip side of the problem, those are sigmas. Okay, so that's the flip side, but this was a pretty effective way of studying nature, you know. Collect data and then carry out some really simple computation with subtraction, nothing more, and then turns out there's some insight there, right there. Okay, so let's go with okay, so the new data illustrated. Okay, so then let's make it slightly more general. We assume throughout that the increments of time are equal. So we call it h. You might remember that that letter was used in fact in calculus 1. Remember in the definition of the derivative. Okay, so that's the denominator, and so we go a plus h is plus 2h, and maybe into the future, but they progress in equal intervals, and whether we're not taking that limit or not, we don't care about right now. So that's the temporal variable. The spatial variable will depend on time, Okay, so whether it is known or not, or whether that function is specific or not, you can easily imagine that there is no formula for the locations. It's just it literally could be data flowing to you. Okay, so there's a computer and it is to be computed what's going on, but there is no formula. Okay, so literally there is some kind of detector of your maybe altitude of an object, and then it is being fed to you, and so there's no, you cannot just look at calculus 1 and start integrating something or differentiating something. There is no formula. Okay, so in that kind of a practical situation, then this is what we are doing. Okay, so the special variable there is some unknown function here that depends, that only defined in these points that we call nodes. Okay, and that function is either to be analyzed as we did here, or maybe do something else with it. So displacement is that what delta stands is for if f is our allocations, then taking the difference, we have a bunch of displacements. So that's what we plotted, and if the denominator is equal, if h is equal to 1, we end up with nothing, or we also end up with velocity. Okay, so that's the velocity. Okay, so right now, once again, examples we looked at were almost exclusively h is equal to 1, so this is just to keep it simple, but there is no trouble for us to take that same example and introduce and make t change, any increment that we want, not 1 necessarily. And so the computations will be complicated. How much more complicated they're going to become? Not by far. This is it. This little division over here is the only thing that we contribute that complicates things in comparison to what we have done. Okay, it's called the difference quotient. And of course, you remember that the limit of the difference quotient is the derivative. H goes to 0, so that's arrow. What? How do I finish this? Arrow. So right now we're still doing the what I call discrete or incremental calculus, but nonetheless, let's keep an eye on what we already know, and that's the calculus as we know it. So difference quotient, arrow. What does that arrow stand for? What does the arrow in calculus stand for? The arrow in calculus, well, the notation varies, but it stands for the limit. And so you may have used a lot of this, LIM, but really it's the same thing, and I think it's sometimes this notation is better. So df dt as h goes to 0, okay? So, all right, so it's a coin. Calculus is a coin. On one side we have differentiation, on the other side we have differentiation, integration. Okay, we're not doing neither one of that. We're still doing the stuff that is entirely incremental, but nonetheless, so these are the coins. Okay, so we're doing segments. So a different problem now. We know the velocity and we want to find the location. So we wipe out what we have done now, and we move because we have data, but the data means different, the exact opposite thing. Now we have 30 data points, and they represent velocities. Okay, so once again, it looks exactly the same. Look at it, the column of time moment and then the column of numbers correspond to each moment of time. So we can plot it in exactly the same fashion, just highlight, insert chart, okay? But the problem that we're trying to solve is different. So and then when we ask to describe describe what's going on, we're doing something entirely different. So can you describe what's going on? Okay, I'm almost out of time, so let's answer the question. Then these are the velocities. So just read the velocities, roughly speaking. What's the velocity in the beginning? What?
Increasing.
The velocity is increasing from what value?
0.
0. So you start from nothing, then accelerate, and then what? Accelerate, and then what?
acceleration.
right? And then
Negative acceleration, or like decreasing.
decelerate, right, towards zero once again. And so basically, in the beginning, you're standing, and you gradually accelerate, then reach for a moment the highest velocity, and then decelerate, and then stop in a very gradual manner. Okay, so that's a verbal description, but then we were gonna do the computations so that we wouldn't have to keep guessing. Okay, so I'll stop here, class dismissed. If you have a question, I'm here.